Yeah, I know.
I do the ball.
Just like interesting.
It's for there's up and downs and let's see, right?
Yeah, I think
There's for
All right, guys, let's get started. Okay, cool. So if we look at handout D, I'm going to use my iPad today because my laptop doesn't want to cooperate. All right, so handout D, and let me get to that right place. Yeah, here we go. It doesn't have all the solutions because I think I said one, excuse me, 1 through 6 all. But for number 1, hopefully you guys can see that that makes sense. Average rate change is yeah, you subtract the y values, which are I guess 91 and 70, subtract the x values, which is of course 10, divide it, and so that means you expect an increase of 2.1 degrees Fahrenheit per hour on average from the interval from 4 to 14. So that's how you want to interpret it. You want to interpret it in that manner. So that's important. Oh, gotta be kidding me. Really, now it works? Okay, hold on. Ridiculous. All right, hold on. So I feel better doing this on my laptop. Okay, we're gonna end this. All right. When? Oh, goodness. Sorry. Okay, and this is not the file I want. Now let's actually get to the files. Okay. So because I know the full solution is not shown, I'm just going to kind of go through the questions with you guys. I mean, some of them are shown. We could kind of go back and forth, but I'm going to have to work out 2, 3, 4 with you guys. Okay, cool. Recording. Okay. So number 1, again, I was just discussing it. You guys know what's up there. So 1's fine. And then the part B part, we haven't talked about it. And I know, Sophia, you were asking about it. So I know I explained it too. But when you have a table and you're asked to find derivative from a table, you don't have an equation, obviously, right? Should you make an equation? No, don't. Because you could try going to Desmos if you want and actually making a table and like trying to do some sort of regression model. But we're not an AP Stats class, right? So don't worry about that. And by the way, I mean, how do we know if this is linear or some other type of equation you use the model? Like maybe you use like a quadratic model or something else. We don't know, right? But don't worry about it because all you're trying to do is estimate t prime of 8. So you already know the y values at 6 and 10. So why should we choose 6 and 10? Because 6 and 10 are symmetric, right? They're on equal but opposite directions of 8. So you're doing something called symmetric difference quotient, like the calculator does when it calculates the derivative. Of course, the calculator goes 0.001 to the left and to the right. We're going 2 left and 2 right. That's a very crude approximation, but it's good enough because you kind of imagine if you were to plot the points, say at 6 it's over here and 8's over here, and the curve does something kind of like, I don't know, something kind of crazy like that. Sorry, I meant to say 6 and 10, my bad. So again, the curve does something kind of crazy. We don't know what it's actually doing. And at 8, maybe that's a tangent line. The hope is that the secant line would be pretty darn close. It should be a good approximation. So if you do the secant line through 6 and 10, that should be a way to approximate the derivative of 8 because 8's in between 6 and 10. Did you have to use 6 and 10? No, you could have done you could have further out if you wanted to. You could have done like 4 and 12, if you wanted to. But then you're going too far out, and that might make it too crude of an approximation. So try to pick points that are close enough. So I know I didn't talk about that, but that's what you do. Does that make sense to approach that? Two should be very, very straightforward. I'm sure you guys did that right. Um, I could go through it. Do you guys want to go through any of those, or you guys feel confident that you can do these derivatives correctly? You know, one way you can verify your work, by the way, in the TI-4 calculator, you can actually, whatever derivative expression you get. So actually, someone wants to tell me what they got for, someone want to tell me what they got for part A. Someone just want to fire away. Tell me what they got. Who's brave?
-19 divided by 3x minus 2 squared.
Okay, do you guys agree? Okay, cool. So what can you do to verify this in the graphic calculator? If you go to your TI-84 calculator, I'm sure you can do this in Desmos, but I haven't really explored Desmos enough, so it's a little hard for me to do that. And this is so annoying, all these ads. So you could just graph the derivative. So again, Charlie got -19 divided by, was it 3x minus 2?
Mhm.
To the second power. Okay, that's what Charlie got. Then I'm also going to do this. Alpha window or math, and I can't remember which option it is. But if you do n deriv of the equation that you're given, and the equation, if I hit alpha y equals, I could put as a fraction too, or just use parentheses. It's totally up to you. What was the top again? Is it 2x plus 5? It was?
Yeah.
Okay, cool. And then down below, it's 3x minus 2. And then you're going to say x equals x. So it does it for all these x values. And they should be the same graph. There's the first one. And see how the second one's tracing it? That's how you can verify your work. You can verify your work in this manner. Initially, the test I wrote, I was going to make it non-calculator. But after doing this, I'm kind of leaning towards letting you guys use a calculator to give you that confidence that you guys are doing the derivatives correctly. So maybe. I don't hear any objections to this idea of mine. No objections? Okay. You guys want to be challenged? And no, but you see how the calculator, you can use that to verify your work. So that's a good option, just so you know. Okay. So I'm still mulling exactly. I mean, I could just write a brand new test tomorrow. No, just kidding. I did a lot of work for it, but I might make some tweaks like that. I don't know yet. So, but definitely by tomorrow, I'll have the finer details about the test for you guys, so you guys can use the weekend and start preparing. So anyway, you can use that to check the other work. For part C, same thing. You just got to find the derivative and then determine the slope of the tangent at the points. So you're going to find two different derivatives, right? One at x equals 0 and one at x equals 1. And then, of course, that's it. That's all you do. So they're asking you to find f prime is 0 and f prime 1. That's all this question is asking you to do. And by the way, you can verify this going back to the calculator again. So if I go back to the home screen, alpha window, option 3. And what was it again? Was it 4x over what? So 4x. And it will first at x equals 0. So did you get that? Yes, no? Yeah. Well, why does it say 3.9999999? Yeah, it's an approximate. So the four is fine. And then if I repeat that, and by the way, if we repeat, you could just hit second enter. It'll put the most previous entry, just grab it. I think that's how you do it. Yeah. And x equals 1. And now it's giving me scientific notation, but is it really 1 times 10 to this -6 power? Or is it, what is it going to really be? 0, exactly right. Remember, it's an approximation. So again, you can use that to help you too. For number 4, yeah, we've seen these already. Now this one, a calculator would not help you, right? Would not help you because this is like hypothetical scenarios, like, oh, well, U prime is this and U is this, right? So you would have to kind of just go through the motions and just work it out. We could just take a consensus, make sure everyone agrees. I want to share the answers for A and B. And then if anyone disagrees, then I'll work it out. If not, I'll just assume everyone's good.
-10 and -20.
Okay. Any disagreement? What was that? I'll do B. So you have 3u prime minus 4 and then bracket u prime v plus uv prime. And you're doing this at 2. Obviously, these are all in terms of 2. So 3u prime is -4, so you get -12. U prime v, that's -4 times 1. And uv prime is 3 times 2, which is 6. So -12 minus 4 times 2, which is -20. So I would agree, Charlie. Good job. Okay, we're good there. All right. Now, yeah, I do have the answer for 5 and 6. For 5, well, it's a question for 5. It's asking if it's differentiable. Got it. Okay. At what locations? At 1 and 3. Okay. So these are the boundaries. So always want to check for continuity, which it is continuous at 1. Then for check for differentiability by taking the derivatives. If I take derivatives, you're not gonna get the same thing. Because you'll get 2 different values. You get 1 and -1. So those are not the same. Then you check for continuity at 3, which is not continuous, so forget about that one as well. But at different reasons. The reason for 1 is because it's a corner. It's continuous, but they have different slopes. The reason for x equals 3, it's not continuous. When you're not continuous, you're not differentiable. Okay, and then finally for 6. Ooh, I love this problem. Okay. I didn't do one like this on the last test. I will now. It is on the test. Expect a problem like this. So you've been given a heads up. So what do you have to do? You have to look for continuity first. The quick and easy way is just plug in 1 and set them equal to each other. So 2 is going to equal a plus b. But whoop-de-doo, how am I going to solve for b and a, right? If I have one equation, 2 variables, right? I can't do it. So the next thing you have to do is then take the derivative and then set those equal to each other, and again plug in 1 for x. If I take the derivatives, I get -1 as the derivative for the top function, and the other one's going to be 2ax plus b. And I plug in 1 again, so I get 2a plus b equals -1, and I have my previous equation, which is a plus b equals 2. So now you're solving a system of equations at this point, right? And when you solve a system, then you can get the constants that will guarantee both continuity and differentiability. I love these questions. This is one of my favorite questions. It's a very common AP style question as well. Like a good multiple choice question. But of course, this will be free response for you guys. Very good.
Can you just go through part B again a little slower? Like, I don't get how.
Oh yeah, no, I did it fast. I'm sorry. Yes. So let's look at the original function, right? What's the derivative of the top function? We have 3 minus x. What's that derivative? It's what's the slope of that function? So it's just gonna be -1. You can do the power rule, by the way, but what's the power rule you do for 3? It's just 0, right? It's constant. And for -x, it's just -1. Because there's an exponent of 1 that goes to the front, and you drop it by 1, it's still -1. So that. Now for this one here, don't worry about the constants. Do the exponent to the front and drop that by 1. That's why I get 2ax. And then plus bx, just plus b. So 2ax plus b. So now you plug 1 in, you have 2a plus b. And 2a plus b equals -1. That's how you get that.
Why would like
Because you want this to be differentiable and continuous at x equals 1. That's why. Because that's the whole intention of the question. So yeah. So okay, so that was like a really good review of the homework. Everyone's okay now? The homework? Okay, cool. And I'm glad it records for the other class because they probably need to see that. All right, so now let's go to the notes. Let's do really deep stuff on linear motion. This is going to be a great discussion on physics. I think I love this. And I'm going to see if I could sneak in some of the trig stuff also. If not, we'll have to spill over till tomorrow. But I think I could try to get it all done today. We'll see. even with the little delay I had with the technology. But the most important thing, we got to talk about linear motion. And the questions I'm going to do are also going to be on our test. And I'm going to ask these questions. So I think I'm going to jump to page 36. Sweet. Okay. So it's a one last consideration, but these are a pretty big consideration. So velocity describes how fast an object is traveling and also the direction it's going. So speed is only how fast it's traveling. So when you're driving El Camino or 101 or 280, is there a velocity limit or a speed limit? Yeah, direction does not matter, right? Because you could say, well, the velocity, like, well, no, hold on, my velocity is -50 because I'm going the other direction because my frame of reference, maybe going north is positive, south is negative. Like you're going back home to Redwood City or San Mateo, I don't know. It doesn't matter. It's just, momentum, for example. Have you guys learned about momentum in physics? Right? When you have a crash impulse, right? And you have collisions. Well, yes, it does use velocity in some ways, but when you are looking at the impact, we have to do the absolute value velocity or speed because that's going to cause these collisions. I mean, that's going to tell you the impact of the collision, right? So velocity, whoop-de-doo. It still comes down to speed. And speed is the absolute value velocity because speed does not include direction. Um, so for example, this particle, not as fun of a question as like, talking about collisions, but here's your position function. It's a cubic function, whatever. It's fine. It's given to you expanded and factored. Doesn't really matter. You're asked to find where the particles are the following times. That's really easy, right? Just plug it in. So for part A, that's easy peasy. That's just S of 1. Then we gotta get S of 2. Then we have to get S of 4. Well, S of 1 is going to be 4. S of 2 is going to be 2. S of 4 is going to be 4. And don't forget the units, by the way. But yeah, we do have units. Yes. So you guys say meters also. So be mindful about that. So pretty easy, right? Okay, displacement. Very simple concept. If something's being displaced, you're looking at how much it moved, right? The change in position, right? That's all it is. Displacement change in position. So displacement is delta S, or in this case, I want S of 4 minus S of 0. What's the displacement here? I assume I do speak yawning language, so it's 0 meters. Now, this is where I have a little fun with this. So, for example, like some of you guys have wearable devices that track your steps. I use like, Peloton and another one, I use all these different things. But, if I'm walking this way, my displacement's 0, right? But did I burn some calories? Did I cover some steps? Of course I did, right? So my distance and my displacement are two different things. My distance was probably 10 feet. I walked 5 feet that way, 5 feet back. So I walked some steps. I burned some calories. Or another good example, like, yeah, like I usually go for these early morning walks. I leave my house and I go around like the Bay Trails by road shores. I walk around the Nob Hill Shopping Center, the Bay Club, 2.5 miles. Okay, I got to get, pretty good exercise, right? But my displacement's 0 though, right? Because I come back to my house, right? I don't just stay somewhere out there, right? So we want to make sure we understand that difference. And that's going to play also a key role in understanding the difference between velocity and speed as well. So that's displacement. It's a change in position. Now average velocity, that's easy. That's just S of 4 minus S of 0 over 4 minus 0. And that's super easy. That's just 0 over 4 or 0 meters per second. So on average, the velocity is 0 on average because you get back to the same place. Clearly, there's been some movement, right? And again, if I plot this, the plot looks like this, by the way. It has x-intercept is 0, and another one at 3, and the graph looks like this. And there's a bounce. And that's wait, did I make a mistake somewhere?
It's a 0, 0.
Oh, I'm good. Hold on. No, I'm good. I'm good. So one's over here and four's over here. My apologies. We're good. I was looking at 0 and 3. My apologies. Because that's 0 and 3. So if I find the average velocity from 1 to oh, wait one sec. Um guys, I told you I totally did. Okay. Do you guys see what I did wrong? I did something terribly, terribly wrong. Well, S of 0 is not 4, right? I did S of 1 accidentally. My apologies. Okay. And you know how I caught myself? I looked at the graph. The graph looked weird, right? Because S of 0 is right here, and that's 3, and where's 4? So I really want this, right? That's clearly not a slope of 0. That's a slope of something else. So I know I made a mistake. Okay, what is S of 1 going to be? Sorry, S of 0. My apologies. 0, right. S of 0 is 0. So that's 4. So that's 4. So it's 1 meter per second. My apologies. Okay. S of 0 is 0. Okay. I should have asked that first. That's how I got all screwed up. Okay, we're better now. But A, B, and C. Okay, cool. Now, what is the velocity? Now, in this case, I do want to take the derivative. And the thing is that I'm going to use expanded form because this form doesn't really help me so much. We have to use product rule and some other things like, let's just look at the expanded form. So that's where the expanded form is advantageous, right? So we'll call this S prime of t, or we call it V of t, same thing. V of t is S prime of t. So now let's plug 4 in. Yeah, you should have 3 times 16 minus 12 times 4. Those should cancel, plus 9. So 9 meters per second. And if I plug in 2, that's 12 minus 24 plus 9. But the speed is 3 meters per second. Because remember, that's the absolute value of velocity. Now let's sketch the graph of V of t. You can actually factor out 3 from this, right? Does that make sense? And you continue factoring further. Okay, so now you're actually starting to see. I mean, I know it's not super practical, but you're starting to see kind of a real life scenario where factoring could help. Because by factoring it, where are my x-intercepts? And by the way, if the velocity at 1 and 3 is 0, what does that mean from a motion perspective if velocity is 0? Are you moving? You stopped. You might be turning around, but you got to stop, right? Like if I want to do a U-turn, like I mean, obviously I could do it kind of crazy and reckless, especially in the rain. Don't want to do that, but ultimately, my car has to stop for a moment before it turns around, right? So you have to stop momentarily. Yeah, all these things I'm telling you, please don't do in real life. It's really dangerous. So you have this and this. What's my vertex going to be? At 2 comma something, right? 2 comma what? If I plug 2, what do I got? -3, right? Yeah, you get -3. So when you become more well-versed in algebra, you can do these problems, pretty easily, right? And at 0, the initial position is 9. By the way, am I going to look at anything to the left of the y-axis? Am I going to look at any negative x values? Why? Yeah, unless you have a time machine. Do we have a time machine? No, right? So you're not going to look at that, right? So good. You understand physics? So this is why we call it physics. You're looking physically what's happening, right? So super exciting stuff. All right, so you got this. Okay, so we can see now that at okay, cool. So that's my velocity curve. Okay. Um, okay, so yeah, so there's a sketch. So when does the particle change direction at t equals 1 and t equals 3? And how do you know? That's because velocity is 0. That's how you know. We say you're at rest at velocity equals 0. Also, velocity changes sign there too, right? V goes from positive, negative, negative, positive. Okay, average acceleration now. Acceleration is a derivative of velocity. Or if you want average, you're going to do v of 2 minus v of 0 over 2 minus 0. What's v of 2? Yep, and v of 0 is 9. And you're going to put as meters per second squared. And it kind of makes sense because you don't have to decelerate to get from here to here, right? I mean, you're slowing down clearly, right? So we have to have a negative acceleration. And then, of course, we're going the opposite direction. So fine. But that's what's happening at that one. Okay, we're cool, G. Okay, then Hij. So my equation was 3t squared minus 12t plus 9. So acceleration is the derivative of velocity. Now, what was my velocity equation to begin with? Yeah, 3t squared minus 12t plus 9. What's the derivative of that, guys? 60 minus 12. Yeah. So A of 1 is negative 12 meters per second squared. A of 2 is 0 per meter squared. Now, if you think about it, wait, did I make a mistake? Oh, you're right. Sorry. I can do calculus. I can't do simple arithmetic. I apologize. So, okay, that makes sense, right? Because again, you're decelerating at 1. But when you get to 2, remember our graph looked like this? The vertex is at x equals 2. What's the tangent line at the vertex? What's the slope of that tangent line when you're at the vertex? 0, right? And that's going to be true for any curve. Whenever you have peaks or low points, the tangent lines are horizontal. So now you can find these high and low points because the derivative is 0 there, right? So if you take the derivative set equals 0, you can find these horizontal tangents. That will enable you to find high points, low points. You can do polynomial functions more accurately. We're going to talk about curve sketching in our third unit after we finish this test next week. We'll kind of wrap things up with like calculus. And after Spirit Week or after spring break, we're going to start working on sequences and series. I know you guys at Mr. Band's class. I am going to ratchet it up significantly to really challenge you guys because I got to get you guys thinking more critically. And then we'll do the more calculus type of sequence series that you'll see in Ms. York's class next year. But just a heads up, our most challenging is definitely going to be when we come back from spring break. Just get ready for that. It's going to be, but it'll be good. You guys need it. But I have to push you guys a little harder. Okay. When does a particle have a velocity of 24? Well, what you have to say is when. So you have to set 24 equal to the velocity formula, right? And then just solve by factoring. So what would I do at this point? Probably factor out 3, right? That might be easier. So it's got to be 5. So it takes 5 seconds because you're not gonna report a negative answer, obviously. Okay, cool. Then finally, the last one's pretty easy. 12 equals 16 minus 12. 24 equals 6t. T is 4. 4 seconds. Okay, so definitely expect something like that where I'll give you an equation and you work it out. Now, how can you use a calculator to verify your work? What would you do? Ideas? Just everything we just did so far. All 10 of these parts. Yeah, so but here's right. So you could totally go to the home screen and do the derivative of all these, of the position function and then do the derivative again to get the second derivative and so forth. You do all that work. One thing I would recommend though, and this is definitely good AP technique, and it's why we still are using the graphic calculator instead of Desmos. I still am not a big fan of Desmos for the AP, and I think Ms. York will agree with that when you guys take a class next year. I much prefer you guys go to y equals and put the original equation under y equals. And then recall that whatever you need down the road. So for example, the original equation was this, right? T cubed minus 6t squared plus 9t. So I'll use x instead. So x cubed, and my short-term memory sucks. What was it again? 6t squared plus 9t. 6x squared plus 9x. So it's already stored there now, right? Now, I can recall it whenever I need. Alpha window, option 3. And then how do you call up y1? If you hit alpha trace, you can call up y1. And they just say, yeah, I want it the velocity at 1. Cool. There you go. Or I want the velocity at like 4. Cool. There you go. Or if you want a second derivative, how do you think I would do a second derivative? What do you think I would do? Let's look at they wanted the acceleration at like what? At 1. Okay, so we should get -6, right? So what do you think I'm gonna do?
Do it at the top, right?
Yeah, so I'm gonna do a derivative twice actually. And alpha y1. Now you gotta be a little careful here. I'm gonna say x equals x because I want an expression for that first derivative. So I'm gonna put x equals x. Actually, I don't know if that's gonna work actually. Come think of it. I don't think it's gonna work. Oh, it did work. Never mind. I lied. It did work. Okay, I get -6. Okay. Um a 2 should have been 0, right? Yeah, okay. It did work. All right. Or let me try one more. If I did 4, it should be 12. Yeah. But you can see if I did this. Why did I give 0 in this case? Instead of x equals x, what is it computing when I do d dxy1 of x equals 4?
Oh, back from it.
The numeric value of the derivative of x equals 4, right? And then that's going to be just a constant, which is derivative of a constant, 0. Of course, it's going to say that. So that actually this did work. So it's kind of cool. So you have all these other ways of verifying your work too. Now, granted, I would much prefer you guys do this. Well, I'm not going to ask you to do it by hand, but it's easy anyway. But what if you get some really nasty equations, right, that you have to work with, right? So that's something that you see often on the AP exam. You do see in the multiple choice part. They ask those kind of questions. Okay, let's do some interpretation. And the more I think about it, I don't think I'm going to get to the trig derivatives today. That's okay. I want to just keep the focus on linear motion. You guys need homework on that anyway. So the trig derivatives, I could blast through it tomorrow, and then we'll start review tomorrow too. So, but let's focus. Let's just kind of stick with this one because this is a pretty long one, and there's still another example I want to get through, and then we can stop there. Okay. Um. Okay, this one here. Okay, you have a snail. And this is different because now we're looking at a velocity graph. Okay. Um, you have a snail, and apparently the snail's accelerating, right? How do I know it's accelerating over here?
Velocity's going up.
It's what? Positive slope. Yeah, positive slope. Okay. And then it stays constant velocity. Then it's slowing down until it gets over here. So what's happening at x equals 7, t equals 7? The snail is stopped. This is velocity graph. But mind you, this is not a position graph. This is a velocity graph. You have to interpret it differently, right? So I call interpreting it. Then all of a sudden it is moving. But now that the snail has gone this way, now it's going that direction, right? Is it speeding up? Well, you're right, it is speeding up, even if it's negative velocity, because what's happening is that the acceleration is also negative too. How do I know the acceleration is negative? The slope of the velocity curve. So this is a key point. This is actually the key. This is the whole key for this example. When the velocity and acceleration are the same sign, you're speeding up. Well, they're opposite signs. You have a positive velocity, the negative acceleration, you're slowing down. It's kind of like wind or current that's working against you, or you're driving. Again, you see the tops, you hit the brakes. Okay, that's kind of bad, right? But when you hit the brakes, are you still moving forward? Yeah, you are, right? And then all of a sudden, you reach the maximum distance in the opposite direction, and then you're slowing down actually from this portion to that portion, and then you start speeding up from. So that's really what's happening. Now, from a speed perspective, you're going to have to take the absolute value. Now, we talked about absolute value as a transformation. When you do an absolute value of a graph, what do you do to a graph to transform it if you want the absolute value of the graph? Do you guys know what to do about this portion right here? Because all those y values are negative right now. But if you're doing the absolute value of the outputs, you flip it exactly. That's how you transform it. That's an absolute value transformation. Maybe you guys talked about to be honest, I don't think we ever talked about that in my class. I don't know if Mr. Band does either, so maybe that's a missed opportunity, but hopefully that makes sense. Is that as a transformation, absolute value around the equation converts all the negative y values to positive y values. And the positive y values just say positive. Of course, that doesn't change. Okay. So now let's answer these questions. So the snail, and actually I'm going to do this. I'm going to get a copy of the notes. I don't want to keep going back and forth. You guys can fill out the fill the blanks in the previous on the next page. I'll just kind of write the answers next to the graph. Okay. So for one, the snail starts with a velocity of 0. So it starts with a velocity of 0 inches per minute. That's going to put in the first blank. And travels for how many minutes steadily? For 2 minutes. Steadily is it increasing or decreasing speed? Increasing, right? Up to what? 4 inches per minute, correct. Okay, cool there. Okay, then snail travels for how many minutes in path 2? 3 minutes. I love it. 3 minutes. And at what speed? 4 inches per minute. There you go. Good. Then path 3. The snail slows down. If that's even possible. Slows down for 2 minutes. Until its velocity reaches 0 inches per minute at t equals 7. Ah, 0 inches per minute. And 4. Now travels opposite direction for clearly 6 minutes. And during that 6 minutes, it's doing 2 things. It's speeding up and slowing down. So for 6 minutes, steadily speeding up. To a speed of 9, yeah. 9 inches per minute. And then slowing down. Slowing down to a speed of 0 when you get to 13. And at t equals 13, the snail is at rest. So a total of 6 blanks there, or 4 blanks. I don't know. Hold on. In the circle, sorry. Yeah. So a total of 6 things we have to fill out there. So he now travels in opposite direction for 6 minutes steadily, speeding up to a speed of 9 inches per minute, then slowing down to a speed of 0 inches per minute, and at t equals 13, time t equals 13, the snail, and I forgot my verb, is at rest. So just using proper grammar, is at rest. Okay, good there? All right. Then find for 5. Find for 5, what's happening there? He now travels in the original direction, steadily increasing speed. We're increasing speed. And for what time interval are we acceleration positive? And what for time interval is acceleration negative? Well, remember, this is a velocity graph. How do you interpret the velocity graph to get acceleration? What are you looking for? Slope, yeah. Now, the slope of a position graph would be velocity, but the slope of a velocity graph is acceleration. Good. So the acceleration is positive, obviously here and here. These portions and that portion. Now, here's what you're going to say. It's a little confusing. With parentheses and brackets. Oh, hold on, Kaden, give me a sec. I'm gonna answer your question. I know what your question is. I'm a mind reader. Tell me if I'm right. You're asking why there's a bracket around 0.
No.
Okay, I'm not a mind reader. Okay. What's your question?
Is it increasing from 10 to 13?
The acceleration. No, because look at the slope.
Even if that's velocity.
Yeah, because the thing is that they're working against each other. It's slowing down for sure from 10 to 13, but your velocity is negative and source is positive. That's why it's slowing down because they're working against each other. I know that's confusing. That's very confusing. Now, why am I not including 2 and 10? Well, the thing is that the acceleration, first of all, are we even differential by the corner? No. And what's my acceleration at t equals 10? Is 0 positive or negative? Neither. So if he's asking for a source of positive, I'm not going to report 10.
I can't include 10, right? Now 0 is okay because I'm using the appropriate one-sided derivative. Like, okay, fine. It's differentiable at 0. I'm just, but usually what the College Board sometimes does for these kind of questions is they just say just state the open interval to kind of avoid that confusion. I think they've gone that direction now because they don't, want to avoid the ambiguity. But you never want to include the 2 and the 10 though, because it's not differentiable there. And then where is your acceleration negative? I'll do red for that. Definitely here and definitely here. Um, and technically speaking, I don't think we'd want to use. And I mean, I'm assuming at 13, it's nice and smooth. I guess I'd have to give some information about that. But you could say from 5 to 10, but I think just to be on the safe side, I'm gonna do this. It looks like a corner, yeah. I think I would give you a heads up as a corner. I'll tell you that. Because that could be a little ambiguous. It's a parentheses. That's just a terrible looking parentheses. Because again, we have a corner there. And remember, acceleration is the derivative of velocity, and we're not differentiable at corners. So, okay. So now here's the big thing. Okay. Can I move the screen, by the way? You guys good? Okay. This is the big thing. This is really what the whole point that I wanted to get across to you guys. Speed increases when velocity and acceleration are both positive or both negative. Speed decreases when velocity and acceleration are opposite in sign. Okay. You good? Okay, cool. All right, last example. We got a few minutes left. Actually, why don't you guys handle this? See how you guys do. This is a rocket. Now this is projectile motion, mind you, because this is a parabola that has a negative leading coefficient, so it's going to do something like this here. So graphically speaking, it's doing this. I would strongly suggest you factor out negative 16t to help you with some of the stuff. But you may want to keep the original as well. X-intercepts are pretty easy to figure out. You may need to use a calculator for a part B, so that might help. And velocity, of course, is going to be negative 32t plus 160. Why don't you guys work it out? Hope you guys are okay at this so far. Now you can see the derivative, how that could help me. I mean, I plotted it, found the x-intercepts, and then found the vertex by taking the average of the x-intercepts. That's not hard. I mean, that's fine. But by taking a derivative and setting it equal to 0, what would t equal if I set this equal to 0? 5, right? And think about it. If you throw something up in the air and it comes back down, does it stop momentarily? Yeah. So velocity is 0 up here, right? This is position, by the way. This is not velocity, this is position graph. But you can use velocity to help you find the vertex. Now you can do that, right? You know that. But I just use some simple algebra to do that. So 400 feet is the highest it goes. Then for part B, I have a velocity function, but before I do that, I gotta find the times window height is at 336, which is somewhere in the middle here. So at 3 seconds, we're on our way up. What's the slope here at 3 seconds? Positive. What's the slope at 7? Negative, right? So it's on its way down. But speed's always absolute velocity, just so you know. Okay, for part C, was acceleration. Well, how do you find acceleration? What do you do? Right. Which, by the way, we know for in real life, it's supposed to be 9.8 meters per second squared for free fall, but in this case, it's 32, negative 32, mind you. It should be negative 9.8, by the way, in real life, because you're always, things are always dropping, right? Correct. Actually, that might be correct. I think that is the correct conversion from meters. Yeah, actually, I think that is correct. Feet per second squared. And when does a rocket hit the ground? Well, that's at 10 seconds. That's easy. We just did some algebra for that one. I didn't have to do the calculus for that. So, okay, perfect. Good. We got a key thing done here. I could totally knock out trig tomorrow. That shouldn't be a problem. Homework, it's gonna be in the packet still. It's gonna be textbook style problems, just so you know. I'll put the details in Schoology right now, so you guys know what to do. All right, I'll see you guys.
That one? Yeah.